One study says the drug works. Another says it doesn't. A third says it works but only in women over 60. Each study is a lower court ruling, limited in scope, subject to local conditions, possibly wrong. The Supreme Court reviews all the rulings and issues a definitive verdict. Meta-analysis does the same for scientific studies, systematically combines the evidence from multiple studies into a single quantitative conclusion. Individual studies are often underpowered, too few patients to detect a modest but real effect. Study A has 80 patients, and a trend that doesn't reach significance. Study B has 120 with a similar trend. Neither alone is conclusive, but combined, 200 patients show a significant effect. Meta-analysis increases statistical power by pooling sample sizes. It also increases generalizability. If the effect appears across studies in different countries with different populations, the conclusion is more robust. The systematic review finds all relevant studies. The meta-analysis statistically combines them. The forest plot is the signature visualization. Each row is one study. The square represents the point estimate, the study's effect size. The square's area represents the study's weight. Bigger studies get bigger squares. The horizontal line is the confidence interval. Wider lines mean more uncertainty. At the bottom, a diamond represents the pooled estimate. The diamond center is the pooled effect. Its width is the pooled confidence interval. If the diamond doesn't cross 0, or 1 for odds ratios, the pooled effect is statistically significant. The fixed effect model assumes all studies are estimating the same underlying true effect. Differences between study results are due entirely to sampling variability, random error within each study. The pooled estimate is a weighted average where each study's weight is the inverse of its variance. Bigger, more precise studies contribute more. The fixed effect model is appropriate when the studies are homogeneous, same population, same intervention, same outcome measure. The random effects model assumes each study has its own true effect, and these true effects vary across studies drawn from a distribution with mean mu and variance tau squared. The pooled estimate targets mu, the average true effect across all possible studies. Weights include both within study variance and between study variance tau squared. This makes the weights more similar across studies. Small studies get relatively more weight than in fixed effect. The DerSimonian-Laird method is the most common estimator for tau squared. When studies agree, low heterogeneity, fixed and random effects give similar results. When studies disagree, high heterogeneity, random effects produces wider confidence intervals reflecting the true uncertainty. I squared below 25% suggests low heterogeneity, fixed effect is reasonable. Above 75% suggests substantial heterogeneity. Use random effects and investigate why studies differ. Clinical practice guidelines typically use random effects by default because the goal is to generalize beyond the specific studies in the analysis. Systematic review finds the evidence. The forest plot displays it. Fixed effects assume one true effect. Random effects allow study-specific effects. Weighting by inverse variance gives precise studies more influence. The diamond is the verdict. Next, what if the courts disagree?